Once upon a time, the people on a very special planet made their first journey into space. The mission was a success and began a new era for the now spacefaring civilization. Just a few decades later, the pale blue dot had become surrounded by thousands of spacecraft doing extraordinarily meaningful work, studying the changing weather down below, providing information to save lives during disasters, and delivering global internet, communication, and navigation services. But something bad is coming that puts all of this at risk. An accidental collision will create a huge cloud of fast-moving debris. A cloud big enough to spread and destroy further satellites in a cascading effect, creating more and more dangerous fragments until the most useful orbits around Earth are no longer safe for spacecraft or people. Before things got too bad, an international committee was set up to address the growing problem of space debris. At that time, spacecraft were being launched without any plan for what to do at the end of their lives, meaning they would one day become debris, potentially crashing, exploding, or falling down to Earth. To fight back, the committee published the first ever space debris mitigation guidelines. To prevent explosions, at the end of every mission, all fuel stored on board spacecraft must be expelled, and batteries should be disconnected from solar panels so they no longer recharge. All satellites flying in low Earth orbit, below 2,000 kilometers, should be deorbited within 25 years following the end of their mission. To do this, operators need to ensure enough fuel is left to fire the thrusters and gradually reduce the spacecraft's altitude, finally causing it to re-enter Earth's atmosphere and safely burn up. Larger spacecraft are often made of big components that could survive re-entry and reach the ground. They therefore require a controlled re-entry, meaning operators ensure the satellite re-enters Earth's atmosphere above specific uninhabited regions. Earth re-entry maneuvers are very fuel expensive and therefore not practical from higher altitudes. Instead, when the mission ends, these satellites should raise their altitude to be left in a graveyard orbit, preventing them from striking functional satellites in this highly productive space highway. Moving spacecraft to these dead zones does not solve the problem of space debris, but for now, it minimizes the risk to functioning satellites. By following these and other simple steps, the amount of space debris in Earth's environment could be kept to sustainable levels, and the future use of space would be secured. Are we, the people on the special planet, following our own advice? It took some time for the guidelines to have an effect, because many missions had been launched already, or were years into development and would need to be completely redesigned. The first major satellite collision unfortunately took place between an operational and a dead satellite. Crashing at a relative speed of nearly 12 kilometers per second, it created thousands of bits of dangerous debris. Multiple exploding rocket parts, and the intentional destruction of some satellites continued to vastly increase the amount of debris in orbit. By the late 2010s, satellites in high-altitude, economically valuable orbits like the geostationary ring, used for communication services, had near-perfect adherence to the mitigation guidelines. But in low Earth orbit, 80% of satellites that should have performed a deorbit maneuver were left undisposed of and abandoned to their fate. Long-term simulations show an exponential growth in the number of objects in space, and a considerable increase in the number of collisions and debris fragments if space agencies, companies, and other satellite operators don't change their behavior. Today, satellites move out of the way of debris fragments multiple times each year through expensive collision avoidance maneuvers. The United States, and increasingly other countries, use an extensive network of debris-detecting sensors to issue hundreds of collision alerts every week for satellites flying in low Earth orbit, including Europe's vital Earth observation satellites, monitoring our planet's land, seas, and climate. Upon each collision alert, extensive work goes into determining the chance of a collision, as well as deciding how best to protect each satellite, how far to move it, and in what direction. If an avoidance maneuver is carried out, the satellite's instruments are often turned off, meaning they can't gather scientific measurements or provide commercial services. Precious fuel must also be used, shortening the lifetime of the mission. These maneuvers are time-consuming, expensive, and complex. But they are nothing compared to what is coming. The era dubbed New Space has begun, and the number of small, privately owned satellites is increasing dramatically. Thousands are being launched in large constellations, huge clusters in the sky working together to provide more efficient, consistent, and reliable services. Several companies have started launching large constellations into low Earth orbit to provide global internet access, and other companies have similar plans to follow. We are now moments away from having more working satellites in orbit at the same time than have ever been launched before. Such constellations have the potential to bring great benefits, but they could also be a source of huge disruption if we do not change the way we act. The current approach to avoid in-space collisions will be impossible in just a few years, and in this new era, even complete compliance to the mitigation guidelines may no longer be enough. We need to do more. Our future in space depends on automated collision avoidance, from assessing the likelihood of a crash to sending the commands to a spacecraft to get out of the way. Automated decisions could even take place on board satellites, informing operators and other satellites of their actions to avoid interfering with planned maneuvers. As these intelligent space systems get more data and experience, they will become even better at predicting how situations evolve, reducing errors as well as cost emissions. ESA is developing technologies for an automated collision avoidance system, as well as methods of refueling, repairing, and upgrading satellites in orbit, extending the lifetime of missions, and potentially minimizing the number of new satellites that need to be launched. ESA is also working on debris removal missions that will fly up to dead spacecraft and debris objects, capture them, and move them to safety, either by sending them down to burn up in Earth's atmosphere or out to the graveyard zone. Solar sails, balloons, and other devices could be added to spacecraft closer to Earth, meaning they catch more of the planet's thin atmosphere and gradually slow down, lower in altitude, and burn up safely. To promote sustainable behavior, the first international space sustainability ratings are being developed to rate planned missions on their potential for debris creation and adherence to international standards, ensuring activities in space can be openly monitored so we can all assess the environmental impact of missions launched to orbit. Our planet is unique, and the rapid and remarkable development of space technologies has allowed us to see this in incredible detail. By reaching into space, we have brought huge benefits down to Earth, providing technologies that enrich our societies, connect people in previously unimaginable ways, and give us an incredible perspective and understanding of our planet. The orbits around Earth, however, are a limited resource. We must extend all that we have learned about the need to take care of our planet up into space. We know what will happen if we continue on our current path, but we also know exactly what we need to do to change that fate. It is time to act, to ensure humanity's access to space is guaranteed for future generations.